to do some algebra, and it ain't 2x plus 2x equals 4x kind of algebra. It is going to be quite intricate and quite messy. So we are looking at essentially, oh good, pretty much everyone's here now, how to find arc length. So if you want to know the length of the curve from A to B of y equals f of x, here is your formula. It's basically the integral of an ugly square root. You can also do a similar thing, you know, when your function is called x equals y cubed, that kind of look. Then you can also get the arc length when the information is given as x as a function of y, and it's pretty much the same ugly square root. So where is this horrible algebra I'm talking about? It's happening right in here. You have to take 1 plus the derivative squared, and you got to make it nice. You got to do style points on it, because if it stays as a square root, unless it's a very, very simple square root, you're going to be in trouble. So I'm jumping right into question 5, where the curve is 1/3 x cubed plus 1/4 1 over x. Actually, they wrote it like this in WebAssign. This is that. I just don't like this because it tends to cause problems with me, and maybe with you. Okay, so I'm going to find the derivative. Well, power rule. Well, that's nice because that times that gets you x squared. And this one's a bit messy. If I want to differentiate this guy, won't I probably have to call it that guy? Would you agree? If you want to differentiate 1/4 1 over x, you should really call it 1/4 x to the negative 1. That's why I wrote it this way. See, if you write it here, if you write it like this, some people unfortunately think that's what it becomes. Do you see how the 4 is stuck to the x, and they think when they move the x, they move the 4? And this is the correct and this is the wrong. So if you're wondering why I do that, that's when I use it. Right, differentiate, multiply by the power, reduce the power by 1. Now, style points, as I call it, are really important in these questions. Can you see what I've done there is just returned the question back to what it looked like, right? Back to its original form. Now, this ugly square root has the derivative squared and 1 added on. So that's what I'm now going to do. It's going to be 1 plus this derivative that we just found squared. So it's going to be 1 plus x squared, take away that guy, right? I guess I could have called that 1/4, but too late now. And since you're squaring it, I'm going to write it down like that. Basically multiplying it by itself. Do you all recognize a FOIL situation here, just with some really weird terms? So f, the first times the first, gets you x to the 4. Now watch this one. Put a little dotted line on it. The outside. I'll do some scratch paper on this guy. You're going to take x squared and you're going to multiply it by negative 1 over 4x squared. What on earth does that become? Anyone got an answer to that? What would that become? X squared times negative 1 over 4x squared.
Negative 1 over 4.
Agreed. So negative 1 over 4. Now, if you come and you do the I, the inside, can you see you just get a negative 1 over 4 again? And then if you do the L, well, this guy who's negative times this guy who's negative gives me a positive answer. And the two guys at the bottom multiplied together give me 16x to the 4. And what I have now is an x to the 4 This guy, and this guy give me a plus a half. And this guy at the end looks like that. Now that is what 1 plus the ugly derivative squared looks like. That guy is going to get put in here in a minute, but not yet. When I finished yesterday, I went and said, if you ever see three things, it's pretty much going to be a perfect square. Now, it's not like x squared plus 6x plus 9, right? Something you can factor very easily. But nonetheless, it is still a perfect square. You only focus on the first term and the last term. Don't worry about the plus a half in the middle. It's going to sort itself out. The x to the 4 gets me x squared plus 1 over x to the 4. Any guesses, any suggestions for what that becomes? 1 over 16x to the 4.
One over 4x squared.
Correct. So essentially, you take the square root of that guy, and you take the square root of that guy, and that's how you find out who these guys are. So if you see three terms, it will be a perfect square, and this is the perfect square. Now, if you don't trust me, take that guy, multiply it by itself, right? Do a FOIL on it, and I guarantee you get this guy. Now, why is that helpful? Well, let's return to the equation for calculating the arc length. It's going to be the integral. Let's check. In this question, it's integral from x equals 1 to 2. Okay, so it's what's the damn thing? It's an integral from x equals 1 to 2, the square root of 1 plus the derivative squared dx. So it's going to be the integral from 1 to 2, the square root of this guy. Now, do you see what really nice thing is going to happen now? Because won't a perfect square inside the square root essentially cancel out? And we're going to be left with the integral from 1 to 2 of just that guy. And if I want to integrate this guy, I'm going to call that x to the negative 2, right? So I can use the power rule. So what do I get? I get 1/3 x cubed, add 1 to the power, and divide by the new power. Evaluated at x equals 1 to x equals 2. And tidy up just a little bit more. Some more style points. And the reason you need to do that is you're going to have to get exact values here. We don't want nothing 0.1234. We want fractions or square roots, whatever it is. And so you really have to write it this format to get that. Right, if you plug in 2, you get 8/3. If you plug in 2 here, you get take away an 1/8 minus. If you plug in 1, you get 1/3. If you plug in 1, you get that. But at least can you see that they're nice fractions? They aren't things like 1/4, 2 to the power of -1, right? They aren't weird looking stuff like that. So let's see what we have. I have 8/3, subtract 1/8, subtract 1/3, and subtract a negative, that's add 1/4. And then just do the usual math, choice 1, and 59/24. That's the arc length in this question. Would you agree there's some really weird algebra going on in this question, like I kind of warned you? Right, so you're going to have to FOIL stuff. You're going to have to deal with quite messy situations, and you're going to end up having a perfect square. Anything about this question before I finally remove it? They are quite long as well. More opportunities to have problems. Now, the next fella I'm going to pick is question 4, or at least similar to 4. And it's 36y squared equals x squared take away 4 cubed. And we're going to be doing it from x equals 4 to x equals 9. Right, this one has an extra step. This isn't really in a form that's going to make it possible for me to differentiate it. So I'm going to subtract 36 from both sides. And then I'm going to take the positive square root of both sides. And the reason I know it's positive is that they had that little thing in the question. So that guy gets me a 1/6. And if you want to take a square root, it's a half power. Are you happy about that becoming this? Can you see where each of the pieces? The 136 gets you 6 and the cube gets you 3/2. Now, this is the function that we are going to find the arc length for from x is 4 to x is 9. So let's find its derivative. Would you agree this is a chain rule derivative question? Chain rule. So multiply by the power. 3/2 times this guy, that gets me 3/12, that's a quarter. Reduce the power by 1, gets you 1/2. Followed by the derivative of x squared minus 4. It's a chain rule, right? So there's an extra 2x there. So tidying it up a little bit, I get 1/2 x squared minus 4 to the power of 1/2. You happy about the 2 and the 4 quarter partially cancelling? Now I'm going to do 1 plus the derivative squared, right? Every time. Now that's going to be 1 plus all of this squared. Now, if you have more than one thing in a bracket being squared, you can square each piece individually. So 1/2 gets me a quarter, x gets me x squared, and that guy gets me that. Are you happy about that? Style points. Do you think I am going to leave this thing looking like this thing? Do you think I'm going to do stuff to it? What do you think?
Are you going to distribute the 1/4 x squared?
I am, and I'm going to get that. Now, this guy has 3 pieces, doesn't it? Right? 3 parts. And isn't my general rule of thumb, if it's got 3 pieces, it is a perfect square? Agreed? What will 1/4 x to the 4 get you when you take its square root?
1/2 x squared.
Agreed. And what, well, I won't ask you, this one is too silly. Would you agree that the 1 just gets you +1? Now, can you trust me that if you FOIL that out, you get this? Whoops. -1. Will you now trust me that if you FOIL it out, you get that guy? Are we cool on that? I'll write that again. It's a bit messy. You get this guy. Has anybody any idea why I needed to change that 1 to -1?
You need a negative x squared.
Yeah. Now, if that had been +x squared, wouldn't +1 be totally fine? So you may have to, you might have to tweak it a little bit, plus or minus, just to make things come out. Okay, now that's good news, because won't the arc length then be the integral from 4 to 9 of the square root of this guy? But that's the integral from 4 to 9 of that guy. Right, now I've got a time crunch here. Can I do ... here? Would you be able to integrate that power rule, plug in 4, plug in 9, and 5 minutes later get 1749, so whatever it is? Are we comfortable but you could finish that off in your run? Right. Now, did you see that was a different kind of perfect square in the sense that, different algebra led you to it? But at the end of the day, if you see 3 guys, will you think perfect square? Think perfect square. Now, we do a little list here for you. Now, what I'm writing down here is I'm going to go through the questions and I'm going to tell you which ones are perfect squares. So you know that you're going to get 3 terms and it's going to, come out the way the 2 that we've done today. So question 2 is going to be a perfect square. Don't know about this one. Let me check it. Okay. We just did 4. We just did 5. They're perfect squares. 6 is a perfect square. Seven will be a perfect square. Eight's 1. 10. 11. Nope. Take it back. Not 11. One last one, 12. By far, the vast majority of questions, would you agree, are perfect squares? Vast majority of them. There are a couple of questions at the end where you're not actually asked to do anything except set them up. So they're just like 1-line deals. So I'm not including them in the perfect square world. So I think what I'm going to do is pick another perfect square, right? A third one. And then we'll show you questions that are not perfect squares, just so you can see the other kind of algebra that can happen. So let's find one where it goes x equals. And why not? Question 6. We have x equals 1/8 y to the 4 plus 1/4 1 over y squared And let me just figure out where the heck I am. Here we go. Can you recognize just the way it's written that it's one of these, right? So I want to differentiate this guy. Basically, I want to differentiate it with respect to y. So multiply by the power, reduce the power by 1. This fella here is going to be called that guy. So when I multiply by the power and then reduce it by 1, I get that. Are we okay with the derivative? Power rule will be a negative. Now, style points. Right. Negative power is called 1 over y cubed. I want to square this guy and add 1. So it's going to be this guy times himself. And if you do FOIL, this guy times this guy gets you 1/4 y to the 6. You then get negative a quarter plus 1/4 1 over y to the 6. And you will be left with, eventually, do you see 3 terms? Agreed? 3 terms, perfect square. That guy and that guy are going to tell me who we need. Okay, 1/4 y to the 6. What does that give us? What goes here?
One half y to the third, or
Yeah.
cubed.
Cubed. Square root, basically half the power, square root of the fraction. Half the power, square root of the fraction. There are plus in the middle, so plus in the middle, then screw it up that time. So what you're looking at is a perfect square. And if you don't believe me, FOIL it out and check it, but it works. So our arc length is going to be from y equals 1 to 2, the square root of all of this. And this gives me the integral from 1 to 2 of a half y cubed plus a half 1 over y cubed. And since I'm going to be integrating, I will rewrite this fella as -3. Okay. Can I do a ... at this point? Would you agree that you should just do the power rule and 5 minutes later you'll have an answer? Are you beginning to feel comfortable with questions that end up being perfect squares, which is basically the 3 that we've done? Right? You differentiate it, you square it, and you add 1, and then you'll end up with 3 guys. And when you end up with 3 guys, you think perfect square. And then hopefully, it flows from there. Okay, what's next? Well, let's do one that's not a perfect square. And there are, well, maybe not quite as many, but there are some that are not perfect squares. And here's an example one, I believe it's, yeah. This is question 7. And the function is y equals the natural log of the secant of x. That's going to be fun. And we're doing x from 0 to pi upon 4. And so the question is, like all the questions are, find the arc length. And let's do its derivative. Would you agree that that is a chain rule? Right? It's a log of secant x. You differentiate a log, you get 1 over the thing, times the derivative of secant x. Who has that handy? What's the derivative of secant x?
Secant x tangent x.
Which is really nice because the derivative ends up just being tan of x. That's kind of nice, isn't it? Nice and neat. Now, I'm going to take this guy, square him and add 1. You see there's a kind of theme, how I do these. In this case, that's not going to be anything that big. It's going to be that. Does anybody here recognize 1 plus tan squared x?
Secant squared.
Yes. So our arc length is going to be the integral from 0 to pi upon 4, the square root of, well, I guess in a way it's a perfect square, isn't it? In a way. And so you've got secant x dx. Now, secant x was added, I think, a couple of weeks back to our standard integrals. And I'm trying to find my own standard integral pile so I can show you. But if not, I'm pretty sure I memorized it. Here it is. Secant x gets you the natural log of secant x plus tan x. You then evaluate it at 0 and at pi upon 4. And so your answer is going to be the natural log of the secant of pi upon 4 plus the tan of pi upon 4. Take away the secant of 0 plus the tan of 0. And I forgot to stick a log there. Okay, this is going to test your knowledge of trig. The secant of pi upon 4 has to be written down as an exact value. You can't write it as 0.707 or 1.414. Not allowed. Does anybody here know what the secant of pi upon 4 is?
Square root of 2.
Oh, that was, yes, it's a short answer. That was a lot quicker than I was expecting. I'm happy about that. Now, it could be I've got it written down in front of me, which is a good idea, but you can calculate it, right? You can find it if you don't know it. So here's one way of doing it. I hope that you all know what the cosine of pi upon 4 is, right? That's a pretty standard one, root 2 over 2. And isn't the secant just the reciprocal of it? In other words, that's what the secant of pi upon 4 is, right? Now, if you rationalize the denominator, you get the answer. So this guy is root 2. The tangent of pi upon 4 is 1. The secant of 0 is 1, and the tan of 0 is 0. So that's pretty much the answer, but it's not. Well, you might think, oh, he's just being nitpicky. He means that. But it's not. He must be really nitpicky then. Because isn't the natural log of 1 0? So it's not that you might get the question wrong. Can you imagine that you might write this, when WebAssign wanted the best answer possible, which is the last one I wrote. So always be on the lookout for style points, right? Make things as pretty as you can think, as pretty as you can do it. Are we good? Any questions about that one before I move on? Right. Let's see if I can find the ugliest question in the world to do, because I think if we can do the ugliest question in the world, right, the rest aren't going to be that bad. There's quite a few candidates here. Let's see what this one looks like. That's pretty good. This one is question 9. Okay, let's do its derivative. Well, actually, let's not do its derivative yet. Don't have to turn things into fractional powers before I differentiate. Okay. What on earth is this guy going to look like when he is finished? That's the question. What's it going to look like? Well, his derivative. It's a chain rule. Multiply by the power, reduce the power by 1, times the derivative. What is the derivative of an inverse sine function? So actually, you can do it this direction. Do you see it? It's this fella. So it's 1 over the square root of 1 take away whatever it is squared. Well, this guy squared is x. So it's a chain rule. The derivative is 1 over the square root of 1 minus the squared times the derivative of this. Okay, that is scarily ugly, isn't it? That is definitely not pretty. And there's a lot happening before this even gets vaguely nice. So all I'm doing right now is taking all of that and writing it down like that. Are you happy about where all the pieces are coming from? Okay. Plus this fella, 2, that's a square root. That's already square root. Now, I don't think I've ever seen lately 2 uglier fractions that somehow have to be joined together. This fraction and this fraction. If you look really carefully, can't this fraction have a square root of x taken out as a common factor? And then pull it out as its own individual square root. Are you okay with that line? Now, if 2 fractions share a common denominator, doesn't that mean that we can add the top together? The numerators, as they're called. And tidy it up. This is style points on stereo. Is there anything else that I can simplify in this fraction? Every little bit helps.
Cancel the 2.
Okay. Looking good? So far, at least. Do that right? I apologize. I got this. There's a 2 here, right? There's a 2 here. Pull out the 2 as a common factor. Okay. Still cancel the 2's. Might not look any better, but it's now correct. We are looking at 1 minus x, okay, the square root of x, the square root of 1 minus x, and that was just to get the derivative. Okay, now 1 plus the derivative squared, 1 plus this thing squared, which you can basically split into 3 things being squared. Right, if you want to square something, right, you can square its individual pieces, which is what I'm doing. Which means I now have 1 plus 1 minus x squared. The square root of x squared is x, and the square root of this guy squared gives me that. Are you happy with that line? That when you square this, you get that. Anything style point cancelling that you can see now?
Cancel the 1 minus x.
And now I'm going to be left with that guy. Agreed? Keep working at it. Let's make it even prettier. Let's style point it or whatever you want to call it. What should we do next? I want this to be better looking than it is right now. Because if I leave it like that and stick it inside a square root, I'm in trouble. So make it prettier.
You could turn the 1 into x over x. So it'd be I guess 1 over x would be the final.
Right. And you're quite right. I'm just putting in extra lines. Can you see what he said? Would you have believed where we started that 1 plus the derivative squared ended up being that guy? Isn't that amazing what style points can do for you? How it can take even the ugliest, sometimes the ugliest thing. So we should be able to get to our arc length. It's the integral from 0 to 1, the square root of 1 plus the derivative, which is that guy. Well, we're not out of the woods yet, but we're darn close to being at the edge of them. Any ideas of a better way to write this so I can integrate?
X to the negative 1/2.
Wow, you've done even more than I was expecting. Yes, you are right. Is it okay to think of it as square root of 1 over square root of x? That makes sense? I'm just filling in some of the lines, which is 1 over the square root of x. Obviously, you don't need every single one of these lines. Well, we might as well finish this darn thing, right? We spent ages on it. I want to take it to the end. Would you agree this is just a power rule? So add 1 to the power and divide by the new power. Do some style points on it by changing into the square root of x. 2 square root of x becomes 2 square root of 1. Take away 2 square root of 0. And for all that hard work, we found out that the arc length was just 2, which is a very simple answer for what was an extremely complicated question. You may well have to go back and look at this video very slowly and pause it and say, okay, I figured out what he did there, then move on a little bit and pause it again until you've got, you've got to grips with what we did to make it happen. Are we good on that question? Can I move on now? Okay, right, where else have we got? Well, let me show you for the time that we've got left some of the homework questions so you can get a feel for how they're asked. And I might be able to talk a little bit about oops, got an issue here. There we go. Just gonna make it a bit bigger. There we go. Right. Find an arc length. Pretty much the arc length, there's a perfect square, there's a whole bunch of perfect squares going on here. There's question 7 that we've already done. This one is a perfect square. Oh God, you remember that one? No, that was not nothing. Right, in this question here, here is your function. What is not obvious is, what's the start and finish value for x in question 10?
-3 to 3.
Right. Do you really even need to know what the y coordinates are in that question? No. Oh God in Himmel. I do not know what that's going to look like. To be honest, I'm pretty sure it's not a perfect square, but who knows? Some weird algebra, but it has to work, right? So whatever it is, it's going to work. There's a, okay. In this question here, won't you have to rewrite this as x equals y minus 4 to the 3/2? And that one's a perfect square. We did something like question 12. Won't we call this y equals all of this to 3/2? And that'll turn into a 2. That's another perfect square. And then we reach these last few questions where you're only asked to set them up. And there are like 1, 2, 3, 4, 5 choices here. And one of these 5 is correct. So won't you take this guy, differentiate him and square him and do the limits from 3 to 6. Okay, since the limit is 3 to 6, isn't that one not going to work? And that one's not going to work, but I'm kicking them out right away. If you differentiate this guy, you get 1 plus 5y to the 4. And I see 1 plus 5y to the 4 squared here. And I see 1 plus 5y to the 4 squared here. But which one of these is the right answer?
That one?
Yeah. Isn't this one missing the square root? So there's only one of them that works, and your job's to find it. So set up but don't evaluate. So this one would be what? The integral from 0 to 2. And then you click on that and you put in your square root and you type in whatever it is. And that's it, right? So good luck with that one. And here's another one. You'd put in what? 0 to 2 and a square root of some stuff. Whew. We did it. We finished in 2 minutes to spare. Am I good or am I good? That was impressive, that you managed to hang in there long enough to do all this. Okay, say hi, everybody. And excuse me. And I'll hang about at the end in case there's some questions.
Thank you.
Thank you.
Okay, good luck with the algebra, guys, because you're going to have a fun time.
Thank you.
Thank you.
Right.
I have a question about the number 9 that we did.
Okay, let me pull this one back. Okay, I got it in front of it.
So
Well-
so I was looking at WebAssign and it's not saying that we need to evaluate it from 0 to 1. How did you know it was from 0 to 1?
If you look at this function, let me put it on so you can see what I'm pointing at, because I'm not sure where I'm right now. Okay, if you look at this function here, it only exists from x equals 0 to 1. If you put it into your calculator, it looks like that. So I knew it was 0 to 1.
Oh,
Just because I knew that that's the only range of x's that work for this function.
okay.
So yeah, that's not clear why it's 0 to 1, but it is.
Okay. Sounds good.
Anything else, or is that it?
That's it. Thank you.
You're welcome. Any other questions from anyone else? Madison, are you good? Kaylin, you good? Then I am finishing off here, guys. Bye-bye.